Hello and welcome to another walkthrough. Now this time it will be Edexcel Further Mathematics, Further Mechanics Paper 1 and Paper 2, May 2025, which I have never seen before. So this is going to be a blind solve for the entire paper under the real exam conditions. So along the walkthrough, I might be making mistakes, which I'll correct if I realize in the walkthrough. But if I don't, I'll annotate the video and I'll try to explain the worked solution and the thought process as simply as possible. At the end of the walkthrough, I'll mark the paper anyway. For those of you who make mistakes a lot of time, you might benefit from seeing me making a mistake and correct it later. So this walkthrough is not meant to just show you the destination of the solutions, but also show you the journey to the destination. If you feel like jumping to a particular question, you can use chapters in the description. Otherwise, stick around. You might be getting some tips along the way. If you are ready, I'll see you in there. So here's the paper. Let's start from the Further Mechanics 1 first. The two papers together within 1 hour and 40 minutes, right? So that's the sitting time that you have for these two papers. So this is basically root J. Yeah, if you take Further Mechanics 1 and 2 together, which is a typical option combination for engineering student maybe. And without further ado, I'm going to start the timer now. Okay, let's go. Number 1 there. Do it here maybe. Okay, a car of mass 1,000 kilograms moves along a straight horizontal road at a constant speed u meters per second. The engine of the car works at a constant rate of 20 kilowatts. The total resistance of the motion of car is modeled as constant force of 1600 newtons. Using the model, find the value of u. Right, so this is constant speed motion. That means sigma f equals 0. Right, so the driving force would be the engine force, yeah, which is P divided by V, yeah, power divided by speed is force there, the engine force, and minus the resistive force being 1600, and this will be equal 0, right, yeah, because the total resistive force is 1600 and this gives a constant speed. Okay, so basically just 20,000 divided by V equals 1600, yeah, and V is just U basically, so U equals, well, let me change that to U actually. Okay, so it's just 20,000 divided by 1600, yeah, that's simple enough. Okay, divided by 1600, is it? Yep. Just checking. Yeah, everything is fine. I mean, I'm just a bit surprised why it's like 3 marks, but anyway, okay, so it's 12.5 meters per second. Yeah. Okay. Yeah, I think I'm happy with that. And now part B, later on the car moves down a straight road which is inclined to the horizontal at an angle that moves down, yeah, so we gotta be careful. That's alpha, and the car is here maybe, moving down. Okay. And then we have the total resistance to the motion of the car is again modeled as constant. So we have again 1600 here as a resistive force. Just going to move the whole thing a little down maybe. Okay. And then what? The instant when the engine of the car is working at the rate of 20 kilowatts and the speed of the car is 8. Right, now we know that it's going down as 8 meters per second. The acceleration is a, so acceleration, I use double-headed arrow, like the double arrow like that. Find the value of a. Okay, so we need to know that other forces acting on the car would be the gravitational force pulling down, and that is very typically mg sine the angle, which is alpha here. Yeah. And because we already consider the resistive force of 1600, that's already non-gravitational, so that's like friction. And then there's also the engine force again. Yeah, engine force being P over speed again. So that's P over 8. So that's just 20 kilowatts divided by 8. Yeah. So sigma F equals ma again. That's the governing equation in mechanics, right? Newton's second law. So 20,000 divided by 8 plus the driving force down the slope, which is the mg sine alpha. So mg is 1,000 G I guess is yeah, 9.8, right? 9.8, and then sine alpha is given to be 1/49. So those two are the driving forces down the plane, equals ma. Oh, forgot to minus the resistive force, which is again 1600. Yeah, and then we have m times a here. So just set up the equation and solve, right? So basically I'm just gonna do the left hand side and all divided by 1000. Yeah, so the left hand side on fraction here like this, 20,000 again, divided by the speed, which is 8 down the slope, and then plus 1000 times 9.8, this is mg sine theta, divided by 49 minus 1600, yeah, and then down here we have dividing by 1000, yeah, so that's 1.1 meters per second squared. Okay, so that's the value of A there. Part B done. Part C, state one improvement to the model that would make it more realistic. Well, I mean, usually what would be the assumption that you make here? If you read the question, it sounds like they modeled something as constant. So the thing that they say they model as, we can say that, okay, it's probably too simplistic, yeah. So like, the total resistance, actually this term depends on two forms of friction, like the friction with the road and the air resistance. Air resistance is kind of like a friction, but not exactly. It's just the force that you create when you go through air, so air particles hitting you along the way. But the greater the speed you go, the more air particles hit you harder. Yeah, the air particles will hit you harder, so that creates more force. That means the modeled constant resistive force here should be not constant. Yeah, so the total resistance of 1600 should not be constant, as it can change with speed, because you have acceleration down the plane, likely it's going to change. Yeah, and that's it. Okay, there you go. That's question 1 done. Easy. Question 2. All right. A particle Q of mass 3m is at rest on a smooth horizontal plane. A particle P of mass m is moving along the plane and collides directly with Q. Okay, so P hitting Q here. Okay, so show that the speed P immediately after. Okay, so I'm just going to make P going to the right like that and Q being at rest here. Yeah. So P is going at U. Direction of motion of P is reversed by the collision. So reverse, well, let's do like this, Vp. Yeah, so that's Up there. Okay, so UQ is 0. Coefficient of restitution between P and Q is E. Okay, so let's have a crack on E first. Yeah, so E, well, hang on. So the speed of Q before the collision is, let me just write, mass of particle Q is 3m and particle P is m. Yeah, so the initial speed of Q is 0, but the final speed of Q would be VQ like this. Because you got hit from the left, you should go to the right. You can't go to the left. That makes sense, yeah? So let's establish the, compute the coefficient of restitution E. So what is E? It's the relative speed of separation divided by the relative speed of approach. Yeah, because when you separate, you might lose kinetic energy. So the coefficient never get quite to 1. Yeah, so the relative speed of separation would be, the subtraction, the relative speed between these two. And we already know that because Vp is going to the left, Vq is going to the right, so you have to add them. The relative speed would be Vp plus Vq in this case. Because if you already construct the direction of Vp going to the left, and if you do minus, like the formula says, that is when you get confused. I mean, you could do Vp like this, but then you will find that Vp, after solve everything, It's going to be a negative value. So why not just make it to the left, because we know that direction of p is reversed. So, but when you do relative speed, yeah, you have to do vq plus vp here, because in the diagram we're going to make vp and vq positive in their respective directions. Okay, so that's why I'm adding them here, because we know that they will separate like that. That's why you need to add them. But if they go along the same direction, you need to subtract them, because this is relative speed, yeah. And then the relative speed of approach would be just up, because you know q doesn't move at first, and we already know that particle p doesn't move anywhere. Yeah, immediately before it's just u, so we just put u here. Okay, so that's the e there. And then this is coefficient of restitution and conservation of linear momentum. Yeah, so it's just u times m plus 0 for the q, and momentum after collision would be, well, negative mvp plus positive 3m vq, like that. And then if you solve simultaneous, you will see that the speed of p immediately after, which is vp here. So we are solving for vp. Let me just take the first equation and simplify. So EU equals VQ plus VP. Because we are solving for VP, so we should make VQ the subject and substitute in the other equation, right? So this is going to be EU minus VP, right? Yeah, and then we're going to sub this VQ as this into the second equation there. So MU, well, M cancel, right? So M cancel. So I'm going to have 0, sorry, not 0, U equals minus VP plus 3, and VQ will just be EU minus VP, like that, yeah? And then you solve for this, make VP the subject. So U equals minus VP plus 3EU minus 3VP. Yeah, like that. So making VP the subject, we would get 4VP on the left, maybe 3EU minus U. Okay, and as you can see, if we factorize everything, we should get what they want there. So VP equals 3. Well, I'm just going to write what they have there because we can factorize to that, right? Yeah, obviously. And that is as required, yeah? Yeah, so just basically coefficient of restitution and linear conservation of momentum. State the full range of possible values of E. Well, E has got to be greater than 0, but should be less than 1. That is the nature of value of E, okay? This is trivial. You need to know this. Well, maximum it can be 1. If it's 1, then it's perfectly elastic collision, which is unlikely in realistic worlds, yeah? But E has got to be greater than 0. You can't have, like, I mean, it's impossible to have negative E, because the amount of energy is always positive, so the relative speed will be positive, right? You can't have negative. Okay, that's the trivial case, but in this case we know that VP must be, in this case I already compute VP to the left, so going to the left that direction means that VP has to be greater than 0, because we know for sure that the direction of P is reversed, so it's to the left here. That means this has to be positive because this is to the left, right? We worked on it like that. So VP greater than 0, that means U3E minus 1 over 4 here greater than 0 as well. So that means 3E minus 1 greater than 0, because we can just cancel 4 and U together. So E greater than 1/3. So E greater than 1/3, but can't be really 1. So the range would be then E less than equal 1, but greater than 1/3. So that would be the kind of the range there. Okay. Now part C, given that E is now a half, well, yeah, that makes sense, greater than 1/3. Find in terms of M and U the magnitude of impulse exerted by P on Q. So impulse exerted by P on Q, so P on Q would be equal to the change in momentum of Q. I mean, you can find change in momentum of P because they are the same anyway, but technically by definition, this should match the change in momentum of Q, right? And the change in momentum of Q will just be mq divided by vq minus uq, yeah? And mq was given to be 3m. vq, well, we can just find vq, but uq for sure is 0, we know that, yeah, before the collision. Now vq, yeah, vq, well, it's just this, eu minus vp, yeah, E times U minus VP. So VQ, I'm just going to write here, equals E times U minus VP. So that's 1/2 U minus, what is VP then? VP is this guy, yeah? So it's just 1/2 times 3, wait, no, that's U, not 1/2. U over 4, 3 times 1/2, right, is 3 over 2. So I'm just going to write everything, minus 1 there, like that, yeah? Okay. And then what do we have here? So 3 over 2 minus 1 is just 1 over 2. 1 over 2 there, yeah? So it's just 1 over 2 U minus U over 8. Because 1 over 2 times 4 down there is 1 over 8. So this is basically what, 3. So 1 over 2 is 4 over 8. 4 over 8 minus U over 8. 1 over 8 is 3 over 8. So 3 over 8 U would be the speed of VQ. And we plug it in here. Yeah. So we get the, yeah, we get the impulse exerted by P on Q, which will be 9 over 8 mu. The magnitude, yeah. That's it. That will be the answer there. All right. So let me just double check everything. So EU minus VP. Yep. And VP will be that. So U over 4. 3 times 1/2. 3 over 2 minus 1 is 1 over 2. 1 over 2 is 1 over 8. 4. 3 over 8. Yeah. I think I'm happy with everything. So let's move on to do question 3 now. Okay. A plane is inclined to the horizontal at an angle alpha, where tan alpha is that. A small block of mass m is held at the point A on the plane released from rest. Initially, the block is modeled as particle air resistance negligible, and the plane is modeled as being smooth. Right, so a plane, right? And inclined alpha, again, inclined plane. Using the model and principle of conservation of mechanical energy, very good. Find the distance of the block from A at the instance when the speed of the block is 7. Find the distance of the block from A. Okay. So A is when it's released, right? Okay, so point A is released here. And then released from rest. So this is U equals 0. Okay. And then we want to find the distance when it's going at 7 meters per second. That's not too bad. The plane, okay, we ignore air resistance. And what about the plane is smooth? Yep, okay, so there's no friction. So basically just gravitational potential energy changes to kinetic energy. More strictly, it is, so we are losing GPE. So GPE lost equals KE gained. Yeah? Energy lost equals energy gain. I mean, energy is not actually lost, it's just transfer. But in this case, we consider the types. So GPE loss is just, so we consider the change in height here, yeah? Well, if I draw that in a triangle sense like that, might be clearer for you. So, like that. So this is the distance moved, the hypotenuse there, the D. And the height change is just the vertical, which is this guy, yeah? So we know that we can put H as D sine alpha, right? Because we actually want to find the distance moved down the block, right? Yeah, not the height change. But the height change can be put as D sine theta, sine alpha here. And we already know that tan alpha is 4 over 3. Again, the triangle trick I would do. So just put everything for 3 like that. So the hypotenuse would be 5, yeah? Okay, so SOHCAHTOA 4 over 3 there on the triangle. So that means sine alpha is just 4 over 5 instead. Okay, so mgh, which is the change in height there, d sine alpha would be 4 over 5, yeah, that's lost in potential energy, equals the gain. Because we start from 0, we are gaining the speed to 7, so that's just 1/2 m times 7 squared. That's it. No other friction, no other loss in energy, so just this. So that means we can calculate the d now. So let me see. Okay, so d equals 1 over 2 times 49, yeah, times 5 over 4, just moving the 4 over 5, and then times 1 over 9.8, just moving the g value down here. And let's just get a calculator there. So 49 times 5 divided by 2 times 4 times 9.8. Okay, let me check the calculator there. Yep, everything should be fine. So 3.125. So I'm just going to put as 3.13 meters then, rounded to sig figs. Yeah, I mean 3 sig figs, sorry. Okay, part B. In a refined model, the block again is modeled as a particle and air resistance is modeled as being negligible. But the plane is rough. Alright, coefficient of friction between the block and the plane being 2/3. Using the refined model, B find in terms of M and G the magnitude of frictional force acting on the block as it slides down the plane. Okay, just same diagram there. But, well, I don't need to draw, right? Because it's the exact same diagram. But now the energy is not just about GPE and KE. So the energy loss is still the same. Yeah. But now the KE gain on the right hand side is not just about the energy gain now. Because you would need to spend some work overcoming the friction down the plane. So this is work done against friction as well. Additional term there. Okay, everything here is the same, so mgd times 4 over 5 again. Yeah, do we find the same thing? The magnitude of frictional force. Wait, hang on. Okay, right. Yeah, let's just find some extra term first. Well, I'm just going to put everything I know first, so 1 over 2 m using the refined model. So we're going to assume that it's the same speed, right? Oh, no. Oh, okay. No, this is not energy yet. So we need to do the plane again. Yeah, so down here we have mg sine alpha. And then up here we have the frictional force, which is mu r, right? And then here we have r, and here we have mg cos alpha. Yeah. So the magnitude of frictional force would be mu times r, but then r is equal to m times g. Cos alpha was 3 over 5, right? Because sine alpha was 4 over 5. Yeah. So I'm just going to write 3 over 5 mg here. So that means friction, yeah, equals mu r equals r, mu was given to be 2/3 and r is just that. So this is simple first. So 2 over 5 mg for the time being, yeah. Okay, magnitude of frictional force. And then we're going to use the energy, work energy principle again. So now we do GPE lost, yeah, at the same speed equals KE gained plus work done against friction. So GPE loss is again distance of the block from A at the instant. Yeah, same thing. So mgh, which is d sine alpha again. So sine was 4 over 5, right? Let me just check. Yeah. And then the kinetic energy 1/2 times 7 square again. Now the additional term, work done to overcome friction. So work done is just force times distance. So the force that is going against as a friction, right, would be this force, 2 over 5 mg. So it's 2 over 5 mg here times the distance itself down the plane. So that's just the additional term there. And of course, we are finding the d here. So mg, m cancel, sorry. Okay, and let's gather the term d there on the left side. So if you move this to subtract that, we would get 4 over 5 gd minus 2 over 5 gd. So that's just 2 over 5 gd, right? Equals 49 over 2 on the right hand side, because it's just kinetic energy. So basically, d is just 49 times 5 divided by 2 times 2 times 9.8. Yeah, this is just d as a subject, basically. And probably it, that's it, right? Yeah. So calculator, 49 times 5 divided by 2 times 2 times 9.8. Let me just double check everything. Yeah, that should be fine. So the answer is just 6.25 meters. And as you can see, it is, it's not smaller. Oh wait, yeah, it's greater. That makes sense, because you would spend a longer distance to go up to the same speed, right? So if there is no friction, the acceleration is greater. So you spend a shorter distance to accelerate to 7 meters per second. But when there is friction, you take longer time, so you take longer distance to accelerate to the same speed. Yeah, just making sense out of it, actually. Number 4. Okay, a particle A of mass m is moving on a smooth horizontal plane. It collides directly with a fixed vertical wall, which is perpendicular to the direction of motion A. Immediately after the collision, the speed of A is 4u. Directed away from the wall as shown in figure 1, the coefficient of restitution between A and the wall is E. Okay, so if we want us to find the speed before the collision, it's just 4u divided by E, basically. Given that the magnitude of impulse exerted on A by the wall is 9 mu, find the value of E. Okay, so again, impulse is change in momentum. So is a VA, is it A, particle A? Yeah, VA minus UA here. We are given that the magnitude is 9 mu, so we're going to put 9 mu here equals m, and V will just be 4u, yeah, 4u, and because the directions are opposite, so when you do minus here, you got to do minus minus, right? If you put 4u as a positive direction, then the initial speed up there, like this guy right here, would be a negative direction, and when you do minus minus, it becomes a plus. I hope you understand that. Yeah. We know that the speed of the initial one here, initial speed times E will be the final speed when you hit the wall. Just as simple as that. Because the wall doesn't move, so it simplifies the coefficient of restitution equation. You just multiply E with the initial speed, you get the final speed, like that. So that means the initial term here, I'm just going to put A here, yeah. The UA would just be final speed divided by E, and the final speed was given to be 4U. You got to know that this is different U there, UA and U there, different letters. So that's why I'm doing 4U divided by E here, to find the initial speed of A, yeah. I'm just going to delete this. Okay, so M cancel there, so 9U equals 4E. Well, let's just factorize 4U out, not 4E, and 1 plus 1 over E here. So U cancel as well. So I get 9 over 4 if you divide 4 on both sides, and this is just 1 plus 1 over E. So 1 over E as a subject is just 5 over 4, right? Okay, and E is just 4 over 5. That should make sense, yeah? Okay, we got the value there already. And what do we have here later? At the instance when A rebounds from the wall, particle B of mass 2m is projected along the plane towards A as shown in figure 2. The particles are moving in opposite direction along the same straight line. When they collide directly immediately before the collision, the speed of A is 4u and the speed of B is u. Okay. Immediately after the collision, total kinetic energy of two particles is mu squared. Determine, showing your method clearly, whether they are there are any further collisions between A and the wall. Okay, right, so if there's any further collision between A and the wall, it means that A must go to the left because the plane is smooth here. So only by a little speed after the collision with B will allow A to meet the wall again, collide the wall again, yeah? So we just do the linear conservation of momentum, conservation of linear momentum between A and B, yeah? And that will allow us to find the direction of A after the collision. All right, so yeah, so now A is for you heading towards B now, like that. Okay. Okay, I'm just checking the information here before the collision speed. Okay, after the collision, total kinetic energy. Okay, so say after the collision, right? If we convert this direction as a positive, let's just say, okay, by the looks, this is for MU, and this is 2MU. So I think let's just say that they all move to the right, because it looks like this momentum is greater. So this will be dominant momentum, yeah? So they'll move to the right. So I'm just going to do, definitely, B will move to the right after the collision, because the momentum of A is greater before the collision, right? So this is 4MU here. So let's make this VA, right? And this is VB, okay? So conservation of linear momentum, 4MU as the initial for A, minus, right, because we can bend to the right as positive, so this will be minus 2MU before collision. And then after collision, I have MVA plus 2MVB, right? Because to the right is positive. Okay, now we can cancel the M, so this is just basically 2U here on the left, and that would be VA plus 2VB. Okay? Yeah? We have no idea about, oh yeah, we do. So total kinetic energy after the collision is that. Yeah. So total kinetic energy after collision, so we do MU squared. This is after the collision, so equals 1/2. The kinetic energy of A would be MVA squared. Kinetic energy of B would be 2M. Don't forget, because the mass is 2M, and VB squared here. You got to be careful. All right. So seems like we have to solve simultaneous here because we can cancel that again. So this would be, if I multiply U across, right, I get 2U squared equals VA squared plus 2VB squared, like that. Yeah? Okay. So how do we solve this? Well, seems like if we square this, is that going to help? Interesting simultaneous equations here. Do we have anything else about this? The particles are moving in opposite directions along the same straight line immediately before for U and U. After collision, total kinetic of 2 pi equals MU squared. Determine showing your method clear whether there are any further collision. We just want to show, we don't need to find, right? We just want to show that if VA is negative, if we know for sure that VA is negative, then we're good. Yeah, that's what we need to do. So we want to show, that's our aim, show that VA is less than 0 somehow. That means somehow you probably maybe don't need to find the values of VA and B if you can't. But I think we can, because we're going to solve it in terms of U, right? Yeah, so basically I'm just going to make, because we want to solve for VA, so I'm going to make VB in terms of VA. So VB equals 2U minus VA divided by 2, like that. Yeah? Okay, and now we substitute that into this second equation. VA squared plus 2U minus VA divided by 2 squared, like this, yeah? Okay, so just solving that, so 2U squared equals VA squared plus, well, because you square the denominator as well, so 2 will cancel with the 4 down here after the squaring. So we have if you expand the top bit too, so you have 4u squared minus 4u VA plus VA squared, and all divided by 2. Yeah, because you still have a 4 down there cancelling with 2, so you get 2. And the top bit will just be expanded like that. I'm just checking while I talk. If you multiply out by 2, you get 4u squared equals 2VA squared plus, yeah, this will be simplified to that. Wait, that should be VA, right? Not AA, like that. Okay. Okay. Don't forget we solve for VA. So this is quadratic in terms of u. So if we move everything to the same side, I have 3VA squared. Yeah. And the VA term would be minus 4u VA. Wait, why did I write A again? VA. And then the u term would cancel. This would cancel, wouldn't it? Equals 0. So that's easy. We don't need to do complicated quadratic there. Right? It's just that. So that means I can factorize VA out. So I have 3VA minus 4u alone here. So VA equals 0 mathematically. And 3VA equals 4u. So VA equals 3 over 4 over 3u. And this is a positive number. Right. Because we don't get it to be a negative number here. Yeah. U was convented to be a positive in the first place to the right. Right. And this u we consider it negative to begin with anyway. So that means this is a positive direction. So this is to the right. Okay. So that means as 4 over 3u is rightward, yeah, meaning that the direction of speed of velocity, direction of motion of P after collision with B is not reversed, yeah, because it's still positive. Therefore, no further collision with the wall. That's it. I mean, it can't go back to the wall now because it's going to the right, and it can't catch up with B anyway, because B will be, I mean, the speed of B, if you try find it, it will be even faster than A, yeah, with the P. Why did I write that? With the wall. That will be the reasoning there. Okay, I think I'm done with that. Let's move on to the next paper. Okay, next paper. I think we're good. Yeah, actually we have more time than that, but okay, there we go. Next paper, paper 2. Wait, not that one, sorry. This one. Okay. Mechanics, further mechanics, paper 2. So this would be the root J for the AS student, yeah? Now let's do it. Okay. A uniform plane lamina shaded in figure 1 is formed by removing the isosceles triangle ABE from a rectangle ABCD. The midpoint AB is M and blah blah blah. I mean, I'm not going to read them all. I'm just going to focus on what's being asked here. Show that the distance of center of mass of lamina from AB is 13A over 5. From lamina AB. Of the lamina from AB, sorry. Yeah, okay. So this is all lamina. Okay. Yeah, it's a composite body. So let's do table, right? So we have a rectangle, the full rectangle. Actually, it's a rectangle, and then an isosceles here. Okay. So the shaded part means that it's actually a solid, like a actual lamina, but the white one is indicating that it's being removed from the actual lamina, right? So it's a basically subtracting lamina. Okay, so, and then I'm gonna do what? Let's do area, because this is lamina, so we do area, and this will be the center of mass, yeah? So we do Y, because this is, vertically above AB. Okay, so this is measured from AB. Okay, so the area of the rectangle is 4A times 3A, so that's 12A squared. And the isosceles here, you need to know, this is just a triangle, so it's half times 3A times 3A, yeah? So that would just be 9 over 2A squared, right? And this is a subtracting area, okay? And then y, right? So for a rectangle, it's just halfway the height, which is 2A then, yeah? Halfway the height, just up from AB. But for the, for any triangle, from the base is 1/3. 1/3 from the base, you need to know that. Or 2/3 from the vertex. So it's 1/3 from AB of the height. 1/3 of the height from AB. So it's 1/3 of 3A, which is just A then. And then after we got this table, we do, so y bar equals sigma YA divided by sigma A, basically. Because lamina center of mass depends on, the area, not the mass, because the uniform density means that we don't need to care about the actual density. We can use the area. So 12A squared times 2A, that's for the rectangle. Now we have to do minus, right? 9 over 2A squared times A, yeah, subtracting, divided by, right? So just the sum of area. Now the area also gets subtracted, so it's going to be 12A squared minus 9 over 2A squared, yeah, and just that. So you're going to cancel, and you're going to get the distance of the center of mass from AB there. So A squared will be cancelled, yeah, like this one, this one, this one, and this one. So we have on top 24A minus 9 over 2A divided by 12 minus 9 over 2 here. Interesting, yeah, okay. So 24 minus 9 over 2, so I make it 48 minus 9 over 2, so 48 minus 9 over 2, and A is outside here, or divided by, if you do the fraction, you get 24 minus 9 over 2. So 2 cancel, you get 48 minus 9 is 39, right? Divided by, that would be 15A. So using 13 to cancel, 3 to cancel, we get 13 over 5A. Yep, as required from AB. Yeah. The lamina is suspended by a string attached to the lamina at D. Okay, so at D here, yeah. The lamina hangs freely in equilibrium. Okay, so if we draw a quick diagram, I mean, it's not like I'm going to tilt the shape. I'm just going to do this instead. So hang at D, and the center of mass is about 2 less than 3A from AB. So that should be a little below point E, and this is the center of gravity. So the downward vertical would be that when you hang it. Yeah, find it to the nearest degree the angle between AD and the vertical. We got to be careful. So AD and the vertical. So it's just this guy. We want to find the angle, which is not hard now. I mean, sometimes they ask you different angle. You got to be careful. But this angle is not hard because we already know that this distance, yeah, is, we found it earlier to be 13 over 5A, right? So, I mean, we can focus on this right angle triangle and find the theta there. So, yeah, this distance would then be what? I mean, let's just draw the distinct right angle triangle there. So this vertical distance is basically this distance here. So that would be 4A, which is the total distance here, minus this distance to get just this part, right? So that is 4A minus 13 over 5A, right? And then the horizontal distance here is going to be the halfway between A and B, yeah, because we know that. It's got to be halfway there because it's symmetrical. So this is 3 over 2A, right? and then we can find the arctan to get the angle there. So that's not too bad. Yeah, I'm just checking. Yep, that should be fine. So what is this actually? It's 4a minus 13 over 5a, so that's 20 minus 13, which is 7, so 7 over 5a, and then we do theta equals arctan of 3 over 2a divided by 7 over 5a, like that. So what is this? Use a calculator maybe. So this is to the nearest degree. Okay, so arctan 3 over 2, yeah, times 5 over 7, because if you flip the fraction there, 5 will be multiplying, and that's what you got. Okay, so this is 46.97 blah blah blah, so I'm just going to make it 47, yeah, degrees to the vertical. All right, that's it. Not too bad, yeah. Number 2. A particle P moves on the x-axis at time t seconds. The velocity of P is v meters per second in the positive x direction. Find the value of t when P is instantaneous at instantaneous rest. So that is when v equals 0. Yeah, just put v equals 0, basically. So 3 minus root 2t plus 1, and we solve. So basically 2t plus 1 square root equals 3. Well, we can square both sides. We have 9 here, yeah. So t equals 4, basically, the value of t. So that's just one value. We got it. Okay. Part B. The acceleration of p at time t seconds is a meters per second squared in the positive x direction as well. Show that a equals that. So a is the derivative of velocity. So we just differentiate that basically. So 3 goes away. Well, we're just going to change that to that first. So this is 3 minus 2t plus 1 to the power of half. Yeah, let's change to that. So this is basically 0 minus 1 over 2, 2t plus 1 to the power of minus 1/2, and then times 2 outside. So that's basically 2 cancel. I get a minus, yeah. Why do I have v minus 3? Oh, okay. This is in terms of v. Okay. Yeah, we have to simplify it. So this is 1 over square root 2t plus 1. Okay, this is a. But they want in terms of v, right? So because square root 2t plus 1 from the initial equation here, yeah, if you make square root 2t plus 1 the subject, you have 3 minus v, right? Yeah, so that means we can sub this into this, yeah? Makes sense? So minus 1 over 3 minus v, and if you expand the minus sign at the bottom, you get, of course, minus 1 over v minus 3 like that as required, which you can do, yeah? All right, so that's part B done. Part C, find the speed of P when it is decelerating at 4 over 3. Now, because we know that we are given that A is directed to the right in a positive x direction, so if we want to find that at which it is decelerating at that, we're going to equate A to minus 4 over 3 first. And solve for V maybe, because that's what we did earlier, so it makes sense to do that. Yeah, so that's basically it. So V would be equal to, if we solve that, so V minus 3 as a subject would be minus 3 over 4. I just move to the other side basically. Or flip the fraction. So V equals 3 minus 3 over 4. So that would be 9 over 4, right? Let me just check the math there. That should be fine. Yeah, so 12 minus 3 is 9 over 4. That means that's the speed. So speed of V is just 9 over 4 or 2.25 meters per second. Yeah, 2.25, yeah. Okay, that's the speed. That's done. Find the total distance traveled by P between t equals 0 and t equals 15 over 2. Why 15 over 2? Interesting. So 15 over 2 is basically less than 4. Okay? That means, oh, sorry, greater than 4. That means the distance traveled will be a competition between the positive and the negative displacements. I mean, the graph might look like this, yeah? If we have V, so when t equals 0, V is positive. So when t equals 0, let's make t 0 here, we get 2, yeah? I mean, if we do the graph there. And because this is a square root function, so I'm just going to make it like this maybe. Yeah, it should look like that, I think. Hang on. Boop. I think, yeah. No, actually, so if you have positive square root there and you flip it, yeah, it should be something like that. It should be, wait, hang on. But this is negative. Negative is that. Oh, it should look like this, no? Yeah, it should be like that. Okay. Anyway, that's just the graph. Not that important. You don't even need to plot, but I'm just showing you that there is a point at which speed is 0, and we found that already. Instantaneous rest, yeah, from part A. So this is at 4 seconds. Yeah, this is initial, t equals 0. That's at 4 seconds, speed is 0. And then you see, I mean, the 15 over 2 would be about 7.5, right? 15 over 2. And you see, if you integrate the whole thing, there will be a competition between this area and this area, so they get subtracted to each other. Yeah? But if we want distance traveled, we need to find them separately, right? Okay, so we need to find the integral of v dt from 0 to 4 plus, yeah, I mean the modulus of integral from 4 to 7.5. I mean, because we know that it's going to be negative, right? So let's put this to, I mean, if you actually do integrate from 4 to 7.5, you're going to get it a negative. So if you want this to be positive, you just flip the bounds to be 7.5 to 4. That's doable. You're going to get a positive, and you don't need to put an absolute sign there. Or you can find the integral separately and just add the magnitude up, yeah, if you are concerned about that. And then, yeah, same v dt. All right. So let's integrate v dt first. Yeah, the indefinite integral. So it's just integrating this function here. Yeah. So you get 3t. So that was a half before. Let me just look at this. Yep, we were integrating, and we're going to integrate this guy. So it's just 2t plus 1. 2t plus 1 to the power of 3 over 2. Yeah, that's just the power rule. And then divided by 3 over 2. And you also need to do reverse chain rule, so divided by 2 here. You need to differentiate the inner function and divide it down like that, yeah? And the minus sign is the same, right? Because we didn't change the sign there. Okay. So, yeah, plus c, of course, but it's going to disappear. You don't need to know c there. So 2 cancel here. So that would be 3t minus 2t plus 1 to the power of 3 over 2 divided by 3, just that. Okay. So that means if I want to find the integrals for both parts separately, I can just plug the limits for each case in. So that would be, distance traveled would be that integral, right? 0 to 4 plus that integral. But from 7.5 to 4 instead, yeah? So as you can see, if you put 4 in and 4 in from both terms, you're going to have to add them up later. So we're going to just do one of them and add them up. Now putting the 0 in for both terms, so put 0 in here, we get 0, 0 in here, we get 1 over 3, yeah? So I'm just going to put 4 in first. So put 4 in, we get 12. So put 4 in here, we get what? 4 in here, we get 8. 8 plus 1 is 9. So 9 to the power of 3 over 2, that is basically 27 if you plug in a calculator. I'm just doing mental math here. Yeah, 27 there. So 27 divided by 3 is 9. Yeah. So 9 here and 12 here. So that's 3. So that's 2 times 3 here because we got 2 from the 4s here. Yeah. And then a minus from the 0 putting in here. So 0 putting in here gets 0. 0 putting in here we get 1 over 1 to the power of 3 over 2. So that's just 1. So that's minus 1 over 3 from the first brackets. And putting 7.5 into these, I'm just going to do the calculator, guys. Yeah, so 3 times 7.5 minus 7.5 times 2 is 15. 15 plus 1 is 16. 16 to the power of 1/2 is 4. 4 to the power of 3 is 64. 64 divided by 3. Yeah. Okay, so that's just it. Can we do fraction? Yep. Minus 7 over 6. So that's just the lower limit here from the 7.5 alone. Let me just double check that. It's like I'm doing a mixed mental math and calculator here. So things could go south, right? 15, 16, 4, 64. Yep, 64 over 3. Yep, I think I'm happy with that. And then we get a 7 over 6 and then we subtract. Yeah. So it's just basically 6 minus 1/3 and then minus 7 over 6. Wait, what? So 9 over 2. Is it not? Yep, 9 over 2. Or 4.5 meters, right? Meters, yeah. Okay. I might have done arithmetics wrong there, but there you go. That's the method. Okay. Yep, let's go to the next one. Number 3. What do we have here? Composite body, right? Right, yeah. In this question, you may quote without proof the formula for the distance of center of mass of a circular arc from its center. Of course, so we can look at the formula sheet. Uniform Y is used to form a rigid framework. Framework, not lamina, in figure 2. The framework consists of 4 straight pieces, A, B, B, C, B, D, A, D. Yeah. One piece is in the shape of the circuit arc of a circle CD, which is this guy here. In the framework, blah, 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 we get all the distance here. Yep. CD is an arc of radius 2A. Yep. Center at B. ABC is a straight line. ABD is a right angle triangle. Yeah. ABCD all lie in the same plane. Good. Show that the distance of center of mass of arc CD alone from AC is 4A over pi. All right. Okay, so just arc CD alone. Now, arc CD alone, right? So we know that if you have a circular arc being like that, and this is angle 2 theta, right? Let me just show you in the formula sheet. Okay, formula sheet here, yeah. So let's go to the mechanics part, which is probably after, yeah, this one. So, yeah, center of mass here, circular arc. Uniform bodies, hang on. Yeah, I think so. Yeah. It's not a lamina. Yeah, it's a circular arc. So, yeah, if that is angle 2 alpha, has to be 2 alpha here. And then it's going to be the distance from the center of mass of the circular arc there. It's just the arc, so this needs to be dotted to not confuse with which one is actually the shape. Yeah, it's just that, imagine a thin wire bent to a circular arc like that. Yeah, so we have the distance from this center of the circle to the center of mass would be r sine alpha over alpha. Okay, okay. So how are we going to use that in the question? Let's get back to the question. Yeah, we know that, well, if we draw that roughly, okay, this will be right to the center, shortest distance, and that will be the distance of, because this is a right angle, so we know that this is 45 degrees, right? And this is also 45 degrees. And that hypotenuse here, this distance here, okay, is, as we got there, r, the radius, times sine alpha over alpha, and alpha is 45. So r is the radius of this circular arc, which is 2a, yeah, and times sine alpha, so sine 45, right? Sine 45 is 1 over root 2, yeah, because alpha is just half the angle, and over alpha, so alpha, well, alpha should be in radian, right? You got to be careful there. So 45 is pi over 4, all right? So that's the red distance there, okay? Now we want the distance of the center of mass of arc CD from AC. So we need to find this distance actually, yeah, d here. So there would just be, sine 45 times that red distance. So d is just sine pi over 4 times that red distance, which is 2a over root 2 divided by pi over 4, right? Yeah, so that would be it. And we should get that, hopefully. So sine pi over 4 is just 1 over root 2 again, times 2a times 1 over root 2 times 4 over pi. We get over pi there, yeah. So root 2 here and here will cancel. Everything will cancel here. Root 2 times root 2 is 2. 2 cancel with that. So we get 4a over pi, yep, as required. Okay, good. Part B. Show that the distance of center of mass of the framework, the whole framework now, from AC is that. The whole framework from AC is that, right? So we need to do a lot of parts there. So let's split into vertical AB, right angle, the hypotenuse AD and BD, yeah. So that's 3 of them, and vertical BC, and the arc CD, yeah. That's a lot of parts. Let me just move them over a little bit. Okay. All right, so we're gonna just do all of these. I mean, we all already know some of them, right? So we're gonna do the length because they are uniform wire, assumingly having the same density of mass. So length will do instead of area like lamina. So AB is 1.5a, AD. AD is, we need to do Pythagoras, right? So AD is square root of 1.5 squared plus 2 squared, and with the a there because they're both a anyway, so we can just take like that. So what is this? 2.5, right? 3 and 4, yeah, 2.5 if you do Pythagoras there. Because I know that you can use 0.5 to cancel, so that's 3 and 4, yeah, that should be right. And that's AD, so 2.5a, and BD is 2a, BC also 2a there, and CD, we already knew that. CD is just an arc, so it's 1 over 4 of 2 pi r, okay, like that. Okay, so that should be pi a, yep. And now the center from direction from AC, I'm just going to do x, so AC is here, whoops, so this is AC and x will be that for each one, yeah. Okay, so for AB is 0, for BC is 0, yeah. For BD, right, BD should be halfway, so that's A for BD. For AD, it should also be halfway as well, because although it's slant like that, but if you measure the direction, the center of mass here should be around there, which is aligned with the center of mass of BD. So that's also A. And the arc, right? The arc, we already got it earlier, so that's 4A over pi for the arc CD. Yeah. And now we just do. So x bar equals sigma XL over sigma L. Yeah. Rather than A, we use L. So sigma XL, well, seems like I have 0 plus 2.5a squared. Just multiply the 2 rows for each column and add them up, right? So the first one is 0, the second one is 2.5a squared, the third one is 2a squared, the fourth one 0, and the fifth one would be 4a squared because the pi cancels there. Okay, divided by the length. So the total length would be all of these. So that is 4, and that is also 4. So 8 plus pi times a, like that. Okay, and then we just simplify. So a will cancel once. So the top bit will be 4.5 plus 4. That's 8.5. A divided by 8 plus pi. Yeah, we can do 7a because 8.5 is basically 7 over 2. So that's 7a over 2, 8 plus pi. And that is as required. Yeah, I got it. Okay, the framework is freely pivoted at A, like hang from A, yeah? The framework is held in equilibrium with BD horizontal. Okay, BD horizontal by an upward vertical force that is applied to the framework at D. Okay, so basically it's just going to look like this, upward vertical, like that. And the center of mass here, you know, if we kind of like get the sense of that, it's probably somewhere here maybe, center of mass of the whole framework. Okay, which is this distance away from the AC. This is x bar. Okay, and now hang at A. Okay, the mass of the framework is m, so this is m and g, right? The magnitude of force exerted on the framework by the pivot at A is kmg, so kmg there. Find the value of k, giving your answer in terms of pi in its simplest form. Well, moments, right? So x bar mg equals f. Well, this distance times the f. So this distance was the distance BD, which is 2a. Yeah. So 2a times kmg, basically. And x bar would just be the whole term here that we got earlier, which is 7 over 2a over 8 plus pi there. Okay. And then we solve for k, giving your answer in terms of pi in its simplest form. So pi won't cancel, but a can cancel here. Mg can cancel, right? Yeah. So that's it. If you move 2 down the other side, you get k equals 7 over 4, and then that's it, 8 plus pi. Nothing much, much different from previously. So basically that's it, right? I mean, just 3 marks, that's why. But let me double check. 2a. Yeah, just these two forces, right? Because you have no other forces. Yeah, probably I'm going to go with that. Yep, okay, so I'm done here. Number 4. Is it the last question? Probably. Maybe. A car is traveling around circular track. The car moves at a constant speed in a horizontal circle of radius r. In an initial model, the car and driver are modeled as single particle. The track is modeled as being rough so that there is a sideways friction between the tires of the car and the track, coefficient of friction mu. The track is modeled as being horizontal. Using this model, the maximum speed at which the car can move around the circle radius r without slipping sideways is that. Okay, so this is looking from the back of the car maybe. That's the back of the car. I mean, if you imagine, so this is exhaust pipe here. So the car is going into the plane here. This is from the back. So you would have, this is the center, right, of the circular track, if you can imagine. So the radius of the circle is r, basically. Yeah. And speed, right? Speed into the plane is then u, going into the plane, maybe. And we have the only force acting towards the center being friction. All right. Now, friction comes from mu r. So we need to know the normal reaction. The normal reaction is basically mg, right? Yeah. So the only force that provides the centripetal force, which is the force that keeps the object in the motion. If you do physics, you should know that too, would be just friction. So we equate the centripetal force to the friction. So m and, well, I'm just going to do v here. Yeah? V is the speed. V squared over r equals the mu and mg, right? Now, because we also given that the maximum speed is without slipping is that, so we can just plug that in. So it's just m over r and then that whole thing, gr. V squared is going to be, gr over 4, because if you square the half root gr, you're going to get 1 over 4 gr, right? So I put that in already, equals mu mg. So the g cancel, the m cancel, you get mu as 1 over 4, as simple as that. Okay. In a refined model, the car and the driver are modeled as single particle. Again, the tracks model as being rough so that there is a sideways friction. Yeah, there was already a sideways friction between the tires of the car and the track with coefficient of friction 1 over 4. Okay, the tracks model as being banked. Okay, banked now. I mean, we're going to take the same model there, looking from the back again. So I'm just going to draw like that, exhaust pipe. We're looking at the back of the car. At an angle theta now, yeah. Okay, coefficient of friction between the track is the same. Okay, using this model, the minimum speed at which the car can move around the circle, the radius r without slipping. So the radius is now this, because you are banked. The radius won't be this distance now, it's this, because you're going like this. So if you look from the back, this will be the horizontal circle, not this, right? Yeah. So that would be the r. Okay. So we have theta there. Okay, so find the value of tan theta. Okay, so well, yeah. Okay, so this is again mg cos theta. If you do plane mechanics here, like inclined plane mechanics, that's mg cos theta, and this is mg sin theta, right? Usually like that, because the mass and the g is the weight. Now we have friction, so friction should be the ones that keep the car up. So friction is going up, otherwise the car will slide down, right? Wait, hang on. You try to go, no, if you accelerate up and up, the friction should be towards the center. Yeah, okay. So we are assuming that this is at limiting equilibrium, where friction should help you keep you in the circular motion. All right, so yeah, this will be 1 over 4 mg cos theta. That's the friction there. Okay, and that's probably it. 1 over 4 mg cos theta, that's the friction. The mg sin theta is the weight component, and that's all you have for centripetal acceleration. Yeah. So again, sigma f equals fc equals mv squared over r. Sigma f towards the center. Oh, hang on, it's not that, is it? Wrong force diagram. I forgot to resolve towards the center here. Okay. Right. So let's say this is a car and the driver. So we need to resolve the force, guys. Let me just get some more detail about the angle here as well. So yeah, we need to do in this direction. So the mg cos 1 over 4 will have to be resolved to that and that. Oh, seems like the r will be changed now, no? Let me think about that again, hang on. So those two are the only forces. Okay. Yeah. So we're just gonna resolve the these two forces. Wait, hang on. These two forces to the center, and also this. This will be resolved to that. Yeah. Okay. So it's 1 over 4. Well, you're gonna have two forces from these two to the left, right? Okay, so we're just going to resolve that to the left. Hang on, let me just, I mean, I don't need to do the weight, right? Because that's going to cancel. Okay, I mean, if I don't consider the weight, because, I mean, you can think of the weight as being directed down, like that, okay? But we need to do the n, so the n here being mg cos theta anyway, and that's going to have to be resolved to the left as well. All right, yeah, so n will be resolved to the left, and 1 over 4 mg cos theta will be resolved to the left too, and that's probably it, just the two sources of centripetal force there. Okay, so towards the left, right, that would be 1 over 4 mg cos theta times, well, resolving to this direction, we have a theta here, so that's another cos theta, plus mg cos theta, that's from the weight component, the normal reaction, but it needs to be resolved to this. So where's the theta actually? So yeah, this is, so this angle is theta, so that means we have to resolve this down to sine, right? So this will be multiplied by sine theta to get to the left, because these two will add up to centripetal force. It's the source of centripetal force, that's what I call them, and mv squared over r here. And r is just this distance, so how do we find that distance? Will it cancel though? Yeah, radius r. Okay, no, that's fine, r, yeah. Wait, is it the same radius r? Moving around the circle of radius r, same radius, yeah, that's fine. We don't need to care about the r there, okay? So yeah, so the m cancel, right? And here we have g over 4 cos squared theta plus sine cos, g sine cos. So that's some math, pure math knowledge around here. And the speed is given to be 4rg over that, so we're just going to square that, 4rg over 35, and then the r down here, where the r will just cancel. G will also cancel, good. So we have what? 1 over 4 cos squared theta plus sine theta cos theta minus 4 over 35 equals 0. That's the equation we want to solve. We want to find tan theta here. How do we do that? Let me just check. The best way to do that, I think we can divide across by cos squared. Yep, and that's going to give us a quadratic equation. So if I divide by cos squared theta, you should be able to know, because I think you're okay with sec tan identity, right? So tan sec squared equals 1 plus tan squared. You should be okay with that. So we're going to get 1 over 4 plus, I mean, if you're not okay with that, you haven't done it, just comment, yeah. I might be able to just show another way out, but this is the easiest way. So if we divide across by cos squared, that's going to be 1 over 4, and this one will be tan theta, right? Yeah, and this will be 4 over 3. Well, if you divide that by cos squared, you're going to get sec, yeah? And you should also know that. And then we can change sec to, you know, the identity that I mentioned. So sec squared theta is 1 plus tan squared theta equals 0. Yeah, this is pure math now. So if I multiply by the lowest common multiple of 35 and 4, just to be safe, 140, yeah. Multiplied by 140 here, I get, that would be 35, right? Plus 140 tan theta. And that would be 4 instead, so that's minus 16 plus 16 tan squared theta. Yeah, we need to solve for this quadratic, guys. So 16 tan squared theta plus 140 tan theta. That feels a bit weird, but okay, I'm just going to go with the flow first. 19 equals 0. Okay, can we use the calculator to check first? See if we have the answer there. 16, enter, 140, enter, 19. That's horrible. Find the value of tan theta. Oh, they just asked for the value. So which one was it? This second one was negative. So if tan theta is negative, that's the second or the fourth quadrant, which is kind of not possible. We want the first quadrant, right? Because angle should be acute. You can't bank too high there. Otherwise, you're going to go the other way. So I'm going to keep doing that again. Whoops, this is negative also. Oh, we're doomed. Something is wrong. Let me just sip coffee. There's something wrong with the math here. Let me just double check. Oh, yep, this should be a negative. Okay, you know what? I'm just gonna, I think I'm okay with the physics there. There's only two forces that would give rise to that. Yeah, so the N, the mg, and the friction. So the N will be resolved up and to the left. That's fine. Yeah. Wait. Yeah, it should be that. Yeah. And then the friction will be resolved to the left, to the center of the circle, being leftward horizontal. And then, yeah. So that would be cos. That would be sine theta instead. Yeah. Cosine. And then they given you v, then v squared. Yeah, I think yeah, I'm gonna go with that. Okay, so just change that to negative. Okay, and everything else is the same, right? Yeah. Oops. Yeah, I saw a positive value. Did you? Yeah, there you go. It was that, right? So tan theta. It doesn't say exact, so we might be lucky. 8.88. There you go. That's a very high banked angle. Because if we do arctan that, we should get like very high. Oh my god, really? So let's do arctan, hang on, 8.8, yeah? So arctan 8.88. Yeah, that's very high. Never seen a road like that banked angle. Maybe a Formula 1 racetrack or something. That's very high. Okay. Yeah. The minimum speed at which the car can move. Oh, minimum. This is not maximum. Oh god. Okay. So minimum means that friction should go up. Yeah. You have minimum and maximum. So maximum is when if you move too fast, you will slip upwards. Minimum is when if you move slower than this speed, you're gonna fall down. So friction will be directed the other way around instead in this case. Not that now. That means we need to change this to a negative value, right? Okay, so that should be a negative value instead. Yeah. Okay. So it's going to be the force that competes with the N, yeah? It's okay, we're just going to change the math here accordingly. So this is minus, yeah? Just easy does it. This is minus, right? And which one is minus then? Yeah, that would become minus there, right? And then minus 35 minus 16, right? Would be minus 51, isn't it? Yeah. And then you have the equation. Yeah. Just double checking everything again. Yeah, everything remains the same technique, same method to solve. It's just the numbers change a little bit. Gonna go with that. So again, doing the quadratic again. So, I'm just gonna find the answer and then show some working using the formula, and minus 51. Okay, here we go. Yep. Oh, that's still high though. Yeah. Okay, what about the other? Oh, this one makes much more sense. We should get this one. Yeah. The car can't bank that high. So I mean the road can't bank that high. It should be small. I'm gonna go with this one instead. Yeah, because if you put arctan 8, that's like 70-80 degrees. That's too high a banked angle, right? So I'm just gonna go with that. Now, I mean, yeah, it feels a bit off, but it shouldn't be in the situation where we need to pick one, but okay. I mean, yeah. -4 times A times C divided by 2 times -16. Yeah, and I'm just gonna go with that. Let me just check all the values again. -16, 140, -51. Yeah, just gonna go with that. All right, guys. And that's it. Okay, that's everything. I still have quite some time, like 16 minutes. But if I did anything wrong, I think I'm gonna just, annotate the video or do it in the correction. So I'm just gonna stop the timer and I'll see you in a bit. Okay guys, I have marked the paper and I nailed paper 1. I got full marks there, so there's nothing to correct there. But I did relatively bad on paper 2, yeah? So we're gonna have a look at paper 2 and go through the mistakes. And I made a fundamentally incorrect like working in one question there, so we'll have a look at those. So the first one is fine, except this one. Yeah, there is a sign error here, so when I substitute 0 to this, I get 1/3, but because this is already a negative sign, so this should be a plus, because it's going to be minus that, so that's a fundamental error there. So if I had a correct sign there, it would have been 31/6, which is the right answer for this one. So I lost 1 mark there. And yeah, this one is a wrong method here. I mean, the reason why it's basically wrong because I misread the question. This is basically the force exerted at the hinge or the pivot and not at the at this point here. So so it says that there is a force, the magnitude of force exerted on the framework at the pivot is kmg, but there is another force, right? The upward vertical force is applied to the framework at D, which is this point. So there are 2 separate forces here. I thought they give you this force, so that's why I did that. But actually, let's correct this work, yeah? Okay, so rather than F being kmg there, we're gonna just totally ignore this because it's not. And the force is actually this, kmg. Yeah, so the given force is that force instead. And as you can see, the force at point D, because this is point D, remember, would be, if you do vertical equilibrium, so it's gonna, because kmg plus F would have to be equal to the weight. So that means this F must be mg minus kmg, right? Because the total upward forces add up to the total downward, right? So that means we have to keep the F like that, and all the F term will have to be changed accordingly. So we'll just take the same moment equation there, but redo it again with the correct force there. Yeah, that's still the weight, so this is still moment about point A, and it's just this side here that we need to change from kmg to mg minus kmg, basically. Just that little change. So I lost 2 marks there, yeah. I got just 1 mark for taking moments about a pivot, but the other 2 marks are lost there. Of course, mg will be cancelled, yeah. So I'm going to get 7/2 a over 8 plus pi equals 2a. Well, in the brackets here we have 1 minus k, right? And then we want to solve for k. So that's going to be a cancelled here. Well, k will just, well, if you expand that, that's going to be 2 minus, well, I can just divide across by 2 first. So I get that times 1 over 8 plus pi. And then on the right side, we'll just have 1 minus k. So k will just be 1 minus that term on the left hand side, yeah? So k is just 1 minus all this, yeah? Or we can do, make them a little simpler there, so 7 over 4, 8 plus pi like that. Well, if you simplify that, I mean, I'm running out of space there, so I'm just going to squeeze a little. Okay, so that would be what? If you multiply this to make denominator the same, right? So that's going to be 32, I'm multiplying out as well, plus 4 pi minus 17 divided by the same thing. Yeah, so that would be what? 15 plus 4 pi divided by 4 times 8 plus pi. Yeah, that should be the right answer there for this one. And then let's go on to the next question, question 4. This is also another one with a huge mistake, hugely wrong, because I made a huge mistake on question B and I lost about 4 marks, I think. Yeah, just to be fair and harsh. So yeah, I got the concept right that the friction should be upwards because we are finding the minimum force here to keep the car on the road and not slipping down, right? Yeah. So the very huge flaw here in the fundamentals is that I assume that the reaction force is mg cos theta. I shouldn't have done that. It's not right. Yeah, it's not right. Because it would have been right if the car is not moving on the road, like stay on there. Because we have to resolve the body first, right? R is not mg cos theta there, bottom line. So we're going to redo the whole thing. Yeah. Okay, so this is the car again. Let's make R just R. Okay. So this is mg. Okay. And this is friction, which we assume that it's acting up because this is the minimum case. I mean, if it's the maximum case, then it would have been down. Okay. So this is just theta here. So, and that is mu times R, right? So these are just the main forces. We have to resolve these forces for circular motion. So you need to aim that to resolve to this direction. Okay? So if you resolve one of them to that direction, I mean, if you resolve the forces to that direction, the other direction you need to resolve would be the vertical. Just as simple as that. Okay? So we already know that this angle is also theta, and that angle, just going to make this a little simpler, theta as well. Yeah, that means on the vertical axis, yeah, we have r cos theta, right? Just the r there. Hang on, this is also theta, right? We have another one here, theta as well. Okay, and mu r would be resolved up, so plus mu r cos theta, no, sine, sorry, sine theta, yeah, that would be put equal to mg, basically, okay, yeah, that would be put equal to mg. So now we can solve r, but let's just not hurry too much about that, because I think we know the mu, right? The mu was given to be 1 over 4, yeah, okay, so mu is 1 over 4, so we can put 1 over 4 there. Yeah, and then let's keep it at that first. So I'm just going to change this to 1 over 4 just to keep the word minimal here. And then the horizontal direction is not in equilibrium. I mean, the vertical is in equilibrium, but the horizontal is not because you have a centripetal acceleration there. That means you need to find the resultant force to the left. And to the left means that we need to do r sine theta. Yeah, just this guy here because this guy is that, so this guy, r sine theta, would be to the left. And then the only force retarding or competing with this is the mu r cos theta, right? So this is minus mu r cos theta equals, and that would be put equal to the centripetal force, which is m v squared over r. Yeah? So as you can see, if you factorize r out from the two equation, right? Let me just do that. we factorize r out, and r will cancel because we don't know r. We don't need to know r because the question doesn't ask r. It asks for the tan theta. So that means I'm gonna eliminate r by doing this. Yeah. So cos theta plus 1/4 sine theta equals mg, and that's equation 1 maybe. Just gonna put that as equation 1, and this is r sine theta minus 1/4 cos theta equals m, and we know the v, right? So the v was, let me just move up here, this. So if you put v squared, if you put that to square, it's going to be 4rg over 35, all right? So 4rg over 35 and over r here, yeah? So r is going to cancel, yeah? And that's going to be the second equation. Now if you divide the first by the second equation, you'll see that r cancel, right? So I'm just going to do the first divided by the second equation here. R will cancel. You put the left hand side of the first, which is cos theta plus 1/4 sine theta, divided by the left hand side of the second, which is sine theta minus 1/4 cos theta instead, like that. And then the right hand side divided by the right hand side, as you can see, the mg will cancel, yeah? These mg will cancel. And then you would have what? 35 divided by 4 instead, just flipping that thing. Because it's a divider there, that's why 4 and 35 swap. Okay, and that's it. Now this is simple. Now you just cross multiply and get the tan. It shouldn't be too hard, right? So we just cross multiply, so 4 multiply left, top left, so we get 4 cos theta. Well, that's nice, you can cancel the 4 there, just have sine theta there. 35 multiplying this, well, we have 35 sine theta minus 35/4 cos theta. Okay? Well, it seems like if you divide across by cos theta, you're going to get tan. Yeah, that's simple. But let me simplify everything first. Or actually, just simplify, right? So you move cos to the left, sine to the right. Yeah, how about that? So cos to the left, we have 4 plus 35/4 cos theta. And that would be just 34 sine theta, simply. And that's it, you get the tan now. So the tan theta will be, you would have to move 34 to this side, right? Like this, to get the tan. Okay, let's use a calculator for that. So 4 plus 35/4, down here we have 34. So that's just simply 3/8. Should have been that all along. Okay, so that should be the right answer for this last one. Okay, and let's do a review. It is a little obvious here that paper 1 is easier, of course, at least from my scores here. Okay, but let's go through them, right? Because paper 1 here, yeah, mostly about collisions and energy. Yeah, it's just collisions and energy. Collisions, momentum, impulse, and energy, right? Not much. But the coefficient of restitution, yeah, is something that you need to be careful for, right? For this one. And again, I noticed that all the papers ask you about the model. Like, how do you make it more realistic? It's not just further maths, it's also pure maths. So maybe you need to get used to answering those questions. How to make the model more realistic. I think it's a good kind of policy here to ask students, how do you make things more realistic? Because, yeah, you want to be realistic about using math and physics to apply to the real world context, right? And that's good. The second one, yeah, just collision here. So make sure you understand A particularly, like how I derived that. So the concept is usually just using the equations from coefficient restitution and conservation of linear momentum. So those are like the go-to equations when you see this question. Yeah, this kind of question here. And this is important. If I didn't put less than equal 1, I wouldn't have got the mark here. Because it's the very important upper limit of E. You can't really exceed 1. Because that would mean that you get more energy than before collision, which is impossible. In a closed system or the collision where there is no external resultant force, yeah, That's Newton's third law. When there is no external resultant force, the action equals reaction. Or hang on, its total momentum is conserved. Yeah, and that's derived from Newton's third law, right? And that fundamentally limits the value of E to just 1. But in this case, yeah, we can find the lower limit, which it cannot be equal to because we know that the speed of Vp must be greater than 0 to go to the left because the direction is reversed, right? And again, definition of impulse should be fine. Number 3, yeah, this is energy, right? Yeah, so it's about work and energy principle. You use energy twice in this whole question. So energy loss equal energy gain in case there is no friction. But if there is friction, you're going to have to add work done to overcome friction on the right part. That's the key there, okay? And yeah, work through the math, just making everything consistent. By that I mean, if you have other distances, like the vertical distance or others, you got to convert it in terms of the distance you want to find, right? And in this case, it's just the distance along the slope. All right, yeah, this one also collision. So this is consecutive collisions, right? Sometimes they just allow them to collide again. So maybe A will collide the wall again and collide the wall back to B again. Sometimes they do that bad, right? That complicated. So this one is relatively fine, okay? Yeah, it's just that the math bit here might be subtle. It's not that obvious because you would need to solve quadratic in terms of U. It's not even a number here. But you need to know that when they tell you a U value here, like, you know, the very simple hint here is that when they do italic letters, you have to look at them as something of values. They are just values. It's just that they would rather not tell you the actual numbers. So M and U are something of known values. They're not unknowns actually. Just think of them as known values, right? So that means these two equations are simultaneous. Well, which one? Yeah. So this one, wait, hang on now. This one here and this one here are two simultaneous equations with only two actual unknowns, VA and VB. U is a known value, right? That's why we can solve quadratically and get the VA in terms of U, because we convented that U would go to the right. This means that VA would go to the right, and because it's going to the right, there's no further collision with the wall. Okay, that's the way to go. And now the second one, yeah, second paper. Yeah, the first question is find composite body in center of mass. Yeah, make sure you understand how to do this fundamental equation here. I mean, it also applies with any other type like framework, you know. This is a lamina, yeah, so that's fine. Later on we have framework as well. And yeah, this is the key fundamental here. When you hang, you just draw downward vertical, which is going to be through the center of gravity. That's the physics there in this question. And then whatever they ask you, so like the angle between what line to the downward vertical, yeah, and I think you just use geometry to solve that. Okay, that's part B for number 1. Number 2, yeah, this is kinematics. So basically, make sure you know V equals ds by dt. Velocity is the rate of change of displacement, and acceleration is the rate of change of velocity. So you can go back and forth using calculus from displacement, velocity, and acceleration there. All right. And the key thing here is, yeah, about the distance traveled, right? You got to be careful about this. I mean, that was the right method. I just made a stupid mistake here about substitution. So sign error there, but that should have been fine. Yeah, everything is fine here. This one, framework, yeah, another center of mass question. Now changing from area, now we have length. So lengths of the wires in each part of the framework will be the kind of like the thing you need to take in the table here. So instead of area, we have length. But some of them have the center of mass at 0, so you just put them accordingly. If you do it like this, you're not going to forget any part. It's gonna take a little time at first, but it's a safe method, and it's hard to make mistake because you see everything clearly and you can trace back easily what went wrong or not, right? And this is just adding up, right? And yeah, actually in part A, you got to know this is given in the formula sheet, so it's just the angle here is 2 alpha, so you got to be careful there. It's not alpha, it's 2 alpha. So it's not like you take this angle to be plug in that angle. You just need to divide this angle by half, just like I did here, because I know that this is 90. So I use 45, which is in radian pi over 2. Okay. And then, yeah, I proved that this is right. And then, yeah, this was a wrong method because I took the force in the wrong term. So the force that they give us is the one at the hinge A. I thought it was at this, so that was wrong. Okay, and I corrected it. So got to be careful there when reading the question. And yeah, I made a fundamentally wrong method here, some fundamental error here about the force resolution. So yeah, the one huge mistake here I made was about the reaction from the road to the car. So I can't say that R equals mg cos theta. I need to solve the vertical and horizontal directions separately and solve them simultaneously and get the value they want, which is by this working here, yeah, would be right. So overall, I think not too out of ordinary here. Everything is, I think, is typical, except that there is one question that the math can be tricky, and that was in paper 1 actually. Was it? Yeah, it's in the collision. And this one is also a little tricky because it's simultaneous between 2 axes, but it should be fine. Like, you don't need to solve for anything, you just have to derive the math and get the tan theta here. So if you have good math skills, this should be fine, hopefully. And that was it, guys, everything. I hope you find this useful if you've watched this far, so please why not give me a follow or subscribe actually. And do find other videos in the channel like further maths, called Pure Paper 1 and 2, and videos gonna keep coming, so guys just stay subscribed and I'll see you in the next video. Bye.